Right. You know how recitations work for the ones that don't. We're starting with a quiz that is on NTU Cool. It should have been unlocked 5 minutes ago, so we'll see. And you have 15 minutes to take it. Okay. And oh, right. Let me set up the rest of the hardware. Problems taking the quiz? It's there? Nice. I mean, problems starting the quiz, I'm not sure about problems taking the quiz. Cannot help with that. Sure. But this is a quiz. Group activity will come afterwards. Promise. All right. Let's get started with the real part of recitation. So what I want to do is basically go through, well, I'm not going to go through the lecture slides since we've already talked about them, or since I have already talked about them, right? You've seen my video. What I'm going to do today is I'm only going to summarize chapter 3 to 5, because we haven't seen each other for 2 weeks, right? So this is the second week. So we should be going all the way to chapter 6, but we're going to put that one into the next recitation so that we are not overextending ourselves. Also because chapter 3 to 5 kind of work together. They're all on the same concept of superposition. And then we're going to talk more about physics and forces next time. So we start in chapter 3 with vectors. And it seems that everybody, 97% get vectors right. And I guess that's simply because there is not that much new things about vectors. They're basically one additional set of equations, right? You have done it in one dimension, acceleration, velocity, displacement, all of what we've dealt with up till now had a direction, but it was only left or right. And now we're giving it another option, which is up or down, and maybe in and out of the plane. Whenever we're talking about vectors, we're breaking it down into their components, and we call these, so we're breaking it down in components in the x direction, the y direction, according to angles, and then we can recover the length and the angle from the components as well. So we can make a vector into components and components into a vector. Yes, and we're giving it units as well. In this case, it's a unit vector. So it has a length of 1, but it's pointing in either x direction, y, or z direction. And we label them as I, j, and k. Not sure why we don't label them x, y, and z. To complain. And they're getting these funny hats on top so that we're denoting these ones are unit vectors, meaning they are not taking part in the calculation itself because they have a magnitude of 1. They're just indicating the direction. And all we have to do is make sure that we're not mixing them unless they are, well, we're going to get to vector multiplication. And so I, j, and k is producing a right-handed coordinate system. So I is the thumb, j is the pointer, and k is the middle finger. So they're not, I'm not sure that there would be another way to put them. So they're naturally forming this kind of 90 degrees. And so you see I, j, and k, it fits. Alternatively, you can say, you will see that another way of doing it is rotating I to j gives you k. It's also a good way to remembering how a right-hand sided screw goes in and out, right? Because you rotate it this way, it goes that way. It's a trick I'm still using. So a right-handed coordinate system. And we will not need the multiplication of vectors much until we get to magnetic fields, which will be in a long time from now. But we should be, just putting it out there. So there's 3 ways of multiplying a vector. Multiplying a vector with a scalar or with a number just means that you're making the vector longer or shorter. Multiplying a vector with a vector gives you a scalar product because it gives you the length of a vector in the direction of another vector. Does that make sense? Basically, you have a projection. You have one vector, and you want to know, well, if I wanted this vector in this direction, how long would it be? So that would give you this length. So that means that the scalar product is a scalar, or a dot product, maybe you call it. So this one is a length. It doesn't have a direction because we already said it's a length in the direction of that vector. So, yes, so L is a. Okay, and so yes, you could just use cosine for that. Okay. Oh. And if you wanted to calculate the components, this is actually much nicer because you would simply calculate ax times bx plus ay times by plus az times bz. Again, this has to be a length, right? So they cannot be vectors in that sum. So that's why this time we're actually adding components of vectors. Okay. And the third option of multiplying vectors is a vector product. A vector product means that we're taking two vectors and we're forming a third vector out of it. So in this case, out of the board. We are saying that the vector has to be standing 90 degrees to vector A, and it has to be standing 90 degrees to vector B, and it has to be standing 90 degrees to vector A. So A and B are forming a plane, right? And so that means that C is standing perpendicular to that plane. So it's useful because if you have two vectors telling you a plane, the other one tells you that's normal to that plane. We're going to use that one when we get to magnetic fields because there the force is acting perpendicular to the magnetic field and the velocity. So you have velocity and a magnetic field, and it means that your force is not acting parallel to the magnetic field and not parallel to the velocity. It's 90 degrees to both of them. But we're going to get back to that. Okay. And you could derive the multiplication by components. Who has never done vector multiplication? So who is bored by vectors? Who has done that in high school? Who has never seen this vector product, this cross product? Who, okay, all right. So we were saying that in order to calculate the scalar product, you would just multiply the components in x direction, in y direction, and in z direction, and then add them up. That's not how we do vector products, like cross products. Instead, here, A cross B means that it's the components that are standing perpendicular to each other, meaning you would take that product and you would have ax times bx plus ax times by plus ax times bz, right? I'll do it one time. So axi plus ayj plus azk times bxi plus byj plus k. So it's a product, and so I have to take all the permutations. So it's axi times cross product exi plus axi cross product byj plus axi cross and so now we're saying that a cross product forms a vector that is standing 90 degrees. So I times I, it's not, they're not standing 90 degrees to each other. So they are getting me 0. I cross j, let's say this is I, this is j, gives me a vector that comes out, k. So this one here, I cross k. So this one gives me 0. This one gives me ax, by, I cross k. These are just numbers, right? So I only have to worry about the unit vectors. So that gives me k. And then here I have I cross k, ax, bz, I cross k gives me I cross K gives me, not J, gives me the opposite, with minus J. And so now I have only done this one. And I've gotten cards that are AX, that are in K and in J direction. Right, so this is the weirdness because I am using the X and Y components to get the I and J components to get the K, get the length in K direction, or the vector in K direction. So the easier way of doing it, so the way that you could do it is simply go through all of them. I'm not going to do that. It's still, like now I have 3 and I would get another 6 components. The easier way of doing it is by introducing a new, well, I mean, I'm not sure if it's easier, but this is normally where people introduce matrices. Matrices are 2-dimensional vectors. So instead of having just a length, like an X and Y and Z component, they would have, like they're more like a table. And so in our case, this one here would be the I, the J, and the K component. And then I would have A X, A Y, A Z, and BX, BY, BZ. And a cross product is the same thing as taking the determinant, or basically finding the solution. So this is an equation system, and we're trying to find the solution of it. The same way that we're trying to find the solution of a product up here. So the way that we're finding a determinant is we multiply this one, and we subtract it from this one. I direction, what would be the resulting one? And it turns out to go into minus K direction. So no worries with news, gonna ease into it. All right, so vector multiplication. So I'm gonna skip that because there's a little bit of review of that. All right. Questions about vectors. Why do we need them? All right. We need them because we're introducing the concept of superposition. Superposition means that we are taking complicated motions, like the projectile motion, and we're decomposing it into components, the same way that we decompose vectors into components. Superposition means it's moving in one direction without you really caring what it does in the other direction. That's kind of weird if you think about it, because it means that no matter how fast you go this way, you could play, I don't know, ping pong or something in that direction. This one will not affect that one. And this is something that I kind of alluded to with reference frames. Right, I was saying no matter how fast your boat goes, your physics is the same on that boat as on the ground, as long as the boat doesn't speed up. As long as your reference frame is inertial, you can just do all the calculations on that reference frame as well as you could do it on any other reference frame. We were saying, for example, our reference frame of being on Earth is not the best one, kind of works, but acceleration would introduce a weird, like could introduce other forces that are not really there. But any inertial reference frame would work. And so that's what superposition means. It doesn't matter if I'm moving with the projectile, for example, or moving along the x direction and just seeing the projectile shoot up and down. Yeah, maybe that's it. Imagine having a toy train. My rendition of a train. It has wheels, I guess. It has a cart. And you're putting a little gun here. Because that's what you do with toy trains. You carry a gun. And you're shooting a ball. shooting your ball. What will the ball do? It will fly up and fly down, right? So it will hit the gun again. If I aim it exactly 90 degrees, it will just plop up and plop down, right? What happens now if the train is moving? The train is moving, and you shoot up the ball, and it falls back down. Will it still plop into the cannon, or will it end up somewhere else on the cart? Understand my little concept, So if the train is standing and I'll shoot it, it comes back to the same spot. What if this train is moving? I shoot it, will it come back to the same spot? It will. Sorry. It's an inertial reference. You're saying all air will kind of drag it away or something, but that's not really, we're not considering air, right? So if this one moves or not, so you're saying at zero velocity it would just plop back, but if you're going too fast, then it would just end up somewhere. So what? That would mean that we are moving with 40,000 kilometers per day, right? So me throwing something up, it should not end up down here. It should end up at the wall, because I'm moving the whole time, right? Where I am this second is like 100 kilometers away from where Earth is in a second. So you're saying I throw this and it will end up over there. It doesn't, right? Because our reference frame is inertial. Like me throwing this one has the same, this has the same velocity component as the train, right? So you might say, well, it's like the train is moving and it has a y component. Yeah, but the ball is moving with the same y component. So as long as we are living on the train that we're looking, it's going to go up and go down. How about if somebody's looking from the outside? How is it going to look for them? Now they're going to see the ball here, and it's flying up and down with respect to the train. But for them, it's going to look like the train moves away, and the ball moved up and down, right? So it's for them, it's going to look like the ball flew that way and flew back into the cannon. Right? The train is moving, the ball is moving. The ball has never left this path, but the train has moved with respect to the observer. So that is superposition. You can superimpose any velocity, any motion onto an existing motion. Right? What if that guy was running? Well, then it would look even like this one would have been even farther away, and this one would have made an even bigger track, right? So superposition means that you can decompose a motion into any reference frame that you want. So, for example, I can say, well, I'm just going to move with the object, my bullet, in one direction. Then it will look like it's stationary in that direction for me, right? And so, when does superposition not work? Superposition does not work if you are accelerating or if you have forces. So when you were saying, well, the ball will not end up in this if you're going fast, you were assuming that there's some kind of force on it, right? Basically, it has to accelerate. Like the ball would decelerate because it's experiencing air drag. So inertial reference frames means they are not accelerating, they're not slowing down. Okay. And so that means that we can decompose a projectile motion into a motion that is just up and down in y direction, and a motion that is just straight in x direction. And so this is just like vector components. So what we're doing is we're breaking down the projectile motion into a horizontal and and the vertical motion. And so now imagine you have your cannon shooting this way. How is that different from cannon shooting up while we're moving the cannon? Right? Basically, you have one motion this way and one motion that way. This motion is a little more complicated than that because you're having a motion minus acceleration. Like there's a force acting to force it back down, right? So you have an initial constant velocity, and its acceleration gets decreased over time until it reaches zero, when it stops, and then it falls back down, right? We have done constant acceleration, and so the velocity depends linearly on time. Yes? And how about over here? This is just v0, well, in x direction. And so the only thing we're doing is we're saying that the velocity in x direction can be calculated from the total velocity by taking the angle. And if you're taking the velocity in y direction, it's just this is the velocity in x direction. The velocity in y direction is decreased by an acceleration, and the velocity in x direction is just a constant, right? If this one was pointing all the way down, what would be the velocity in x direction? It would be the total velocity, because now my sine angle is just 90 degrees. My angle is 90 degrees. Sorry. My angle is 0 degrees. So the whole thing gets v0. Right? Cosine 90 degrees is 1. So if I'm pointing in this direction, then v0x is v0, and v0y is 0. Meaning, how far is it going to shoot? It's not going to shoot at all. It's just going to hit the floor right there, right? What if I shot the other way up, like straight up, angle 90 degrees? Well, then my x velocity would be cosine 90, 0, and my y velocity sine 91. So my y velocity would just be completely 0. And so that means it would reach the highest, right? The y at which it reaches 0 velocity would be the highest. Does that mean it flies the farthest? It doesn't, right? Because I have no velocity in x direction. So I have to find a compromise between the two. I want to aim as high as I can because that gives me the most travel up. But I want to aim as low as I can because that gives me the most travel over. So the compromise is probably 45 degrees. But that's assuming no drag. Well, we'll get back to that. For now, this is common enough that people calculate it, like they write down the formulas so that you just have them lying around. I'm not, I guess, yes. You will get it, for exams, you will get a cheat sheet, meaning you can bring one A4 paper with equations on it. I don't want you to memorize equations. So this might be a useful equation to put on that cheat sheet because it's something where you know where it comes from. Well, my x is the range. This is how far it can shoot. And how far it can shoot is determined by how high I can shoot. How long does it take to get back to the ground, right? Once it hits the ground, that's when it craters, or it doesn't go any farther. So that means that the time that it travels is determined by by only the y direction. How long did it take to go up and come down to 0 again? And so I can get the time that it took to go up and down because I know that y equals v0t minus t half t squared. So I can find out how high did it travel. And I can find out how long did it take to travel that distance twice. And then I can find out, well, since I know now how long it took, this is my t impact, basically, I can find out how far did it travel. X range 0 times t impact. Right? And so, okay. So people derive the formula so that you don't have to do it again. So this would be the range. So you see that it only depends on the initial velocity and the angle at which you're shooting it. And so now you see that you want to make this as big as possible, right? The range as high as possible. So that one should be 1. And that means that the best way to shoot it is sine 90 degrees, but there's a 2 in there. So that means that my angle is only 45 degrees. It also means that the range is determined by the acceleration. And so now you understand why you would shoot farther on the moon, because you get more time for it to go up and down. Right? So there's a picture. So we're going to try that. This is a complicated problem because it combines both vectors and superposition, but most importantly, the math is not that easy. Basically, what we're trying to see is what is the angle at which A and B will intersect. Okay? So I'll give it 10 minutes to start, and then we're going to see how far you got and fill in the rest ourselves. I like to get. Okay, so you know how group activities work. Find your group and argue with them. What's the angle? That's all I know. I think it is. Who wants to discuss about the problem and who just needs more time to figure out the math? Who wants to talk? Who wants me to shut up? I'll take votes. Who wants their peace and quiet? Who wants some, yeah, I'm not sure if I can offer clues, but we can try it together, you know, we can try and figure it out. So, what are we trying to do? We're trying, I'm all for finding time, yes. We're trying to hit, we know two things. We know that the balls are at the same position, y, at the time of collision, and they're at the same position, x, at the time of collision. Right? So, at time collision, two things must have happened. The first one is that B, is that B? Yes. B traveled upwards by 30 meters, right? So, okay, so I know that 30 meters is my distance, and this ball must have traveled there. What do we know about the motion of the ball? It's a constant accelerating motion, right? So whatever the acceleration is in y component, I'm just going to call it AY. I know that it would have to be AY half times t impact. Does it have an initial velocity? Does it have an initial distance? It doesn't. Okay, so, okay. The second thing I know is that they must have been at the same position x. I don't know the position x, right? But I know that this one must have traveled v times t impact. V, how do I do that? V particle A in y direction, in x direction. And this is how far it traveled. How about the other one? I should call this one dy. So the acceleration of particle B in x direction, half times t impact, would have gotten it there too. Right? So I broke the problem down into two components. I know that it has to touch in y and in x direction, but the motion is different in y and in x direction. Particle A has a constant y position, right? It doesn't have any velocity in y direction. So that's why on that side it's 4. It's nice and easy. It's more complicated in x direction because here it's moving with a constant velocity. So you see, the most complicated thing that we could have done is two accelerations in two different directions. So this is already the slightly easier thing. But now the question is, what are the things that we don't know? We don't know two things, right? The first one is we don't know the time of the impact. It's, well, three things. We don't know the acceleration in y or in x direction. How do we get the, let's start with the acceleration in y and x direction. I would like to relate ax to that 0.4 meters per square second. How do I do that? Ax is this component, right? And I have this angle, and I know this acceleration, like the total acceleration. How do I get to that? So here's a trick. The trick that I'm using is, because I can never remember if it's a sine or cosine. You're correct, it's a sine. But the way that I do it is, well, so imagine this one was 90 degrees. Then the total acceleration would be only in x direction, right? So it should be maximum for 90 degrees. So that's not a cosine, that's a sine. So a sine. How about AY? Well, can do the same thing. If the angle was 0 degrees, then it would just shoot up. All the acceleration was in y direction. So it must be A times cosine theta. A particle B. So I can plug that one in, but all right, yes, let's plug it in. So we're getting 30 meters equals A by A B other one is VA, and it only has x direction. So I could call that one 3 meters per second. Don't have to calculate anything. Times t impact equals ax, so a times sine theta times t impact. Wait, what am I missing? A half t squared. I wrote it there, I forgot it there. Nobody caught it. Right? So now I could. So now the question is what I not know. Before I had 3 things that I didn't know. Now I narrowed it down to 2 things I didn't know. I don't know that angle, and I don't know the impact time. So all my math has gotten me to eliminate one unknown. That's kind of nice. Now what do I do? The final answer is theta is something, right? So that means I probably will not be able to eliminate theta. So instead, I should try to eliminate the time of impact. Okay? So what I'm going to try and do is solve, well, not solve. I'm going to rearrange that so that time of impact is on one side, and then I just squeeze it in there, right? So time of impact squared equals 30 meters times 2 over AE times cosine theta. Right? So cosine, yes. All right. And so now I'm plugging that one in. I'm plugging that one in here. Times 60 meters over a e times cosine. This is squared. I was saying this one is 30 meters. This one is here. Okay. Nobody. You see, there's a t impact here and a t impact there. So I have 3 meters. I'm going to divide t impact here and there. Then I should have plugged it there. Sorry, I'll try that again. So we had 3 meters per square second half times theta equals times the impact equals 30 meters per second. I just wrote that one again, and I canceled this against that. This is why it's annoying to keep using numbers. I would have not made that mistake if I had just kept my variables. Would have seen that there's a VT impact over here and T impact over here, right? So this cancels out, and I get T impact equals AX 30 over sine theta times meters per square second over 3 meters per square second. Yeah, okay. So that gives me T impact. And so I put it in here. You'll see why in a second. And this has to do with the hard part of the math. So I'm going to take this T impact and I'm going to put it in there. So I'm getting A, B, 30 meters was X direction. Oh, total. 3 meters times cosine theta times 30 meters per second over sine theta 3 meters per second squared. It's just really annoying to paste the numbers correctly. Sorry, I have what? Yes. I had, so how about we do it with the variables rather than with that? So I'm going to call this one y0, and I keep that. So what I did is I canceled this against that, and what I should have kept, and I'm not sure if I did, is T impact is V over A times 2. And I have V over A times 2. This 2 would end up there. So, but you're right, this is pretty nasty. I should have just stayed here. T impact is V over A dx times 2. And so I can plug that one in there, and I get y0 equals y0 equals a y times b times 2 over a dx squared. Right, this was t, and there's a square. So I can cancel this against this. Not really cancel, I take the 2 out. And so I'm left with 2aby times b over ax squared. And plugging that one in, I get 2 times cosine theta times that was harder than it should have been. So you with me up till here. All I'm trying to do, all I have tried to do up till now is get out the impact, because I don't really care how long it takes. I just care that at impact, x and y are the same. Like both components for both particles have to be the same. At time of impact, the particle B has moved in y direction to hit 30 meters. And at time of impact, particle B has caught up with particle A. Right? It has caught up with particle A. This one was going faster at the beginning, but it's constant. This one is accelerating until it hits it. So these are the two equations that I have. One is, how long does it take for an accelerated, like for a constant accelerated particle to reach 30 meters? The other one is, how long does it, when do the two particles moving at different speeds we want to touch? And so I now have the solution that for a certain, like this angle, for the correct angle, this one should be solved. 30 meters should be 2 times 3 meters times cosine theta over 3 meters over. You want me to put the numbers in? It's going to be very distracting. So now I just have to solve it for theta. You see the problem with that? There's a cosine and a sine squared in there. Cosine and sine squared. Sine squared, right? I'll write it easier. So basically we have, not easier, but just here maybe, 2 times A of particle B times B0 squared. I can take out the A times cosine theta over sine squared theta, or sine theta squared. So all you have to do is now solve for for theta. And that's why I said the physics is hard and the math is hard. The physics was that you have two components and they have to match. we kind of got to that. But the math is hard because I cannot solve for, I mean, I can, at least not by looking at it, solve for sine theta, cosine theta over sine squared theta. Can you? So all we want to do now is get the theta out of that. The correct theta would just make this one to be, like we know all the other numbers, right? We know this is 30 over 2 times 3 meters per second squared over 0.4 meters per second squared. Right, this gives me a number. I can calculate it. 30 over 18 times 0.4. I can do that. 30 over 18 over 0.4. 4.2. What's the unit? This meter cancels against that meter, and that, like that leaves 1 meter here, there's a meter here, so all these meters cancel out. And this has second square on the top, like 1 over second square on the top, and this has 1 over second square. These two cancel out as well. So no unit. Which makes sense, because we're looking for an angle. An angle doesn't have a unit. Good. At least we haven't made a mistake up till now. But we still haven't solved it. Cosine squared over sine squared theta has to be 4.2. So the next step is something you will not have to do in an exam, but probably in a homework or something, right? We have a sine squared here and a cosine. Do you remember any relation between sines and cosines that we could use? One. Very good. Sine squared theta plus cosine squared theta is 1. So then sine squared theta is just, so I have cosine theta over 1 minus cosine squared theta. Right? Sorry, I'll write it up there. So we have gone from solving the physics problem to solving a math problem. But I'm kind of testing how far you can follow so that I can gauge where I have to start next time. Okay, so we have cosine theta over 1 minus cosine squared theta gives me a number. I'm not sure if it's 4.2, but it's just a number, right? All the other things we know. So we have to solve for that one. And so now you're like, we still have cosines in there. I'll just rename them, okay? I call this one x, and this one 1 minus x squared equals 4.2. Just call them differently. Why? Because maybe this one you know, right? Basically, I have x equals 4.2 minus 4.2 x squared. Or if you like it better, 4.2 x squared plus x minus 4.2 equals 0. Or x squared plus 1 over 4.2 minus 1 so that equals 0. Pick one that you like. I pick that one. And now I want to solve for cosine theta over x, right? How did you do that? Quadratic formula. Remember those ones? x1, 2 equals p half plus minus square root of p half minus q. Q or 2q? P quarter. Oh, sorry. P squared half minus q. You're completely not with me anymore. What? Yes? Okay, nice. Questions about that? What am I trying to do? I'm just trying to solve the last part of the puzzle, which is for which theta that's, like, what's the theta that solves it? What's the angle under which I have to aim to make those two collide? Yes? And so, well, I mean, P is 1 over 4.2. I have 1 over 4.8, 8.4. That's minus 1 over 8.4 squared plus 1. And so I will get two solutions. Why do I get two solutions? Because cosine is symmetric. I can calculate, like, cosine of plus x and cosine of minus x is the same, right? Cosine of plus 90, cosine of plus 90 degrees is 0. Cosine of minus 90 degrees is 0. So I will just pick one. I'll just pick plus. I can do minus, but minus is kind of weird. In general, as a physicist, I try to avoid minus because they might end up at negative numbers, and negative numbers are always the ones that we're leaving out anyways. So whenever somebody asks me which root are you going to choose, I'm choosing a positive one because I'm positive. And because I've been born too many times, whenever I take the negative one, that's the one that cancels. Right? So I can solve that, or I can just look at the solution, which I'm going to do right after I click the, oh yeah, I have to note 1134. Okay. So you still have a chance to write it in your, what is it called, the forum, right, the discussion group. Write down your answer if you haven't already. Give you a minute. So so that's what I'm here for, just ask me. So you're saying, how come y0 is this? This is how long ball B took to get there, right? It's an accelerated motion, so it's a half t squared. So this one is E leaves the origin with a 0 initial speed. It's a shot out of the gun, and a constant acceleration a. Actually, that's not out of the gun at all. That's like a rocket. Yes? Okay, nice. So it's a rocket. That's the other thing. Maybe you want to have some kind of mental picture of what you're actually looking at. This is kind of like a pot that has just been sliding. And this one is like a, I don't know, like a Roomba that is moving under its own speed. All right, and so the solution would be, so I will make available the solution to these problems so that you can check your math. The way that I did it over here is I use that part, right? That part instead of going for the simple quadratic formula. Anyways, what it ends up with is 1/2. And inverse cosine of 1/2, we still have, this one apparently is 1/2. Probably I did the 4.2s wrong. Because it should have ended up at 1.5. So, pardon? This is simply all the other numbers plugged together because we were too lazy to keep writing them. The proper way of doing it would have been to put everything here. Why? Because imagine, like me, you get 4.2 instead of 1.5. Then, as a grader, I will be like, well, got it wrong. If you're like, well, it's these velocities, I will be inclined to give you more points, right? Because you just showed that you cannot operate a calculator rather than you don't know physics. One is very different from the other one. Also, here you have to, this is not as trivial as it sounds. This has no unit for a reason, right? We just checked. It doesn't have a unit that makes sense. So you can save yourself a lot of trouble if you just don't calculate with numbers and units. Because if you forget the correct unit here, even if you get the right answer, my grader is going to be like, well, no unit, no real answer. So the proper way is keep your long formula all the way to the bottom, and then in the last step, calculate it and get the wrong number. And you're getting like 95%. Whereas if you make the calculation, like if you do the calculation all the way like they did, you're just going to end up with the wrong number halfway through. And then you keep using the wrong one to get the wrong answers. So 60 degrees. So let's start with questions about this problem. This is kind of a problem like this is on the hard end. This will not be in an exam. But it will not be in the exam because the math is hard, not because the physics is hard, right? So I wanted to kind of gauge your math because this is the first time that we're doing like a hard problem together. So if you're bored by it, then I know I have to go faster. If you're like completely overwhelmed, then I know I have to go slower. Okay, so if you're overwhelmed, that's apparently the average reaction, so no worries. Questions about the physics. Whenever we have vectors, we're solving it by components. That gives us twice as much information, basically, and it means that we have to keep track of both of them, because normally you get to a point where things are just like you have to plug one component into the other component. It's exactly the same thing that we did for that you could have done for projectile motion. Okay. All right. So up till now, we have only considered kinematics. Kinematics means that we are looking at how stuff moves. We haven't looked into why stuff moves. And so we're going to stop kinematics because it's boring, right? It's kind of just describing something without really understanding the origin of it. And that's not physics. It's just applied math. So instead, what we're going to do now is mechanics or forces, right? So everything up till now was kind of just, do you know how to operate math? It's not physics. So I was following the book when I said that we're going to call the mechanics Newtonian mechanics because Newton was the one that invented it. That's at least what it says in your book. I want to add to that Isaac Newton was an asshole. Oh, I got your attention on that. Right. I will back this up with a 5-minute rant. First, Isaac Newton was not a nice person. Already as a child, he wrote in his diary how much he hated his stepfather, and like he just had like fan fiction about how he would kill him. All right, fine. He came from a fairly poor family, so when he went to Cambridge University, it was not to study there. It was to be like a servant or waiter or something in the colleges over there. But because he was very good at building things, he kind of got promoted to like the experiment guy. And it turns out doing experiments was really important for understanding what was going on around us, because many of our conceptions are just based on weird observations. For example, if I shove this one across the table, it will stop. And so no matter what you shove across the table, all of them will stop eventually. So people were always assuming that the natural state of anything is at rest. Because whenever they looked at something, it was at rest, right? And so they're like, well, things don't want to move. That's pretty much, I can agree with that. I don't want to move. Things don't want to move. So people were always considering, well, so a force has to be something that keeps it moving. But then Galileo Galilei actually came up with an ingenious experiment. His experiment was ingenious because it was both simple and pretty accurate. What he did is he moved the ball down an incline, and he put bells on it. So it would just go. This is the original one. the ball would just blink, 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 blink. It had several bells, and you would have like a notable sound, right? And so then he moved around the bells until the blinks would always be in the same sequence, like in the same time difference. He didn't want blink, 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 blink. He wanted blink, blink, blink. Right? So you would have to move the bells until the time difference between each bell would be the same. And so what he found is, well, in the beginning, he would have to move them closer together, and then it would get farther away. But now, if he made the incline lower and lower, the distance between the bells would get pretty much equal. Like the slower the ball moved, the less it accelerated also. And so Galileo Galilei was actually the first one to say, hold on, maybe this natural state would actually be, it's moving at a constant velocity. The unnatural state is it goes faster. But if you just make it go like lower and lower and lower, it's not that it stops, it's that it doesn't accelerate anymore. And so he was the first one to say, well, maybe the natural state is not stop. Maybe the natural state is just a constant motion. Yet we're calling that Newton's first law. Newton was not a nice person because he could not have other people be, have success. I guess, he came from poor background. Maybe he just needed to have attention all the time. But he could not have other people take credit for things. And so he's like, I invented that. And Galileo Galilei was dead by that time, so it's not like he got killed by the Catholic Church for being an asshole too. So he had it coming. He got killed not because people will tell you it's because he was telling the Pope that the Earth was rotating around the sun instead of the other way around. But the Pope was fine with that. The Pope was like, all right, fine. He's like, no, you don't understand. Your Bible sucks. He's like, yeah, I get it. Just, keep it to yourself. Or I don't know, like, you can publish it, but maybe you don't want to make the argument that the Catholic Church is wrong. You can just be like, okay, Earth runs around the sun. You don't have to be an asshole about telling other people that their stuff is wrong, right? And Galileo did, and so he got burned. So, literally. So, anyways, back to this. Newton was not a nice person either, because he was like, no, I invented this. It's at rest. And so, fine. And then the second law, Newton's law is that something that causes an acceleration is force. So he was like, all right, any small change of motion is an acceleration and is caused by a force. And again, he was not the first one to do that. Carl Friedrich Gauss came up with the same infinitesimal change idea. But so Gauss was living at that time, and he was like, hey, you're not the first one to invent calculus. You're not the first one to think about like infinitesimal changes. And, Newton was by that time the director of the Royal Institute of the Royal Society of Science or Astronomy, I forgot. So he was like the main scientific body in the UK. And so he was like, well, let's see what the Royal Society thinks about who invented it. You understand? He was the boss of that place. So clearly they were like, oh, Newton invented it. So not a nice person. He spent the last so he did most of that before the age of 40. Then he spent the rest of his life with two very interesting hobbies. One is to find the Philosopher's Stone. Philosopher's Stone is that magical thing. Who watched Harry Potter? It's it's either the magical thing that turns stuff into gold or lets you live forever. So he was looking for that. Actually, a lot of his contribution is in chemistry. Like not his contribution, his effort went into chemistry. The other thing that he was very fond of was killing people. And you're like, what do you mean? He was part of the of the royal, of the king's effort into avoiding counterfeiting. Counterfeiting means that a coin would be made from gold back then, right? So it had a certain worth, or silver. And so what people would do is they would file off the outside of a coin, make it a little bit smaller, and melt that silver and use it. So that means over time, your coins would get smaller and smaller. And so what Newton did is he put these serifs, the scratches on the outside. Have you looked at your coins? You see they have these ups, like these vertical scratches. It's so that you can see if somebody filed off the outside. And he was not content with just shaming people into not taking, having them deface money. He went as a policeman to find those people, and he was very proud of this accomplishment of having convicted 7 people to hanging because they were counterfeiting. So now I've ranted enough about Newton. What we think now is that it's actually not his fault that he was a not great person, but that in the time he had some illness, and at the time people were treated for basically any illness with mercury. Mercury is a liquid metal, and so people are like, it must be good for something. So they fed it to people like with a spoon. Now we know that liquid metal, like mercury, is giving you hallucinations, psychosis, and making you into a generally not nice person. So maybe it was not his fault, but maybe he was just on drugs. All right, so back to this. We now call everything related to mechanics Newton's laws. We gave him the unit for force, which is a Newton. Let's just keep it at that. So first Newton's law is the natural state of something is moving at a constant velocity. To stop it moving or to make it go faster, you have to apply a force. That's second law. And forces come in pairs. You cannot push something without something else pulling. So that's the 3 Newton's laws. At rest, as long as there's no force acting on it, acceleration is caused by a force. The proportionality between, so it's just force is acceleration times a number, right? That number is mass. So mass is actually not some kind of, some kind of weight, right? Mass is just something that keeps an object from accelerating. The heavier an object is, the less it wants to accelerate. So you would need more force to get the same acceleration, or the same force would not cause an acceleration. That also brings us to Newton's third law, right? Which is we're going to get back to all these. The picture, no, I don't. Okay, any force acting on a body will have an equal and opposite reacting force from where it came. So me jumping on the floor means that the floor is inversely jumping. I'm being accelerated up, the floor is being accelerated down. So why am I jumping high and Earth is not, like, nobody of you felt an acceleration? Because of mass. We're sharing the same force. It doesn't mean we're sharing the same acceleration. I'm 6 times 10 to the 22 times lighter than Earth, meaning my acceleration is 1 billion, 10,000 times more than Earth's acceleration under the same force. But that does not mean that we're not sharing the same force couple. Or diet, if you watch Star Trek. No, not Star Trek, sorry, Star Wars. Who watched the last Star Wars movie with the diet? Okay, I guess you don't have a connection to that. It's a 9th movie, it's been going on since 1974. But for you, it's like, it's a bad movie, why should I want to watch that? Because of history, okay? You watched 8 bad movies, you're going to watch the 9th one. There were only 3 good ones, and they were all coming out before my time. So I started with a bad one, and then you invested in it, right? You're like, man, this movie sucked. The next one cannot be as bad as this. And then they start talking about midichlorians, and it's going to get worse. But that means that forces, we're going to explain today forces as, like we're going to explain physical forces. Next time we're going to explain systems. Systems means any force that is acting on me has to be acting on something else as well. So me and the something else is a system, is a couple. And so the easiest way to imagine that is the concept of normal force. Normal force means that if something is pushing down on a surface, the surface is pushing back up. How much is the surface pushing back up? Well, if it was pushing up too much, it would fly, right? If it was pushing up too little, it would fall through the surface. There would be acceleration through the surface. So that means that the force that the surface is pushing up with is exactly equal and opposite to the force that I'm applying to make it go down. So in this case, it's its weight, and now it's its weight plus me, right? So this is a systems force, if you want, because we use it in a way that we keep this on the surface. We're not worrying about where it comes from. We're just like, it's equal and opposite. And so it's called a normal force because it keeps stuff 90 degrees normal, right, to the surface. And so that means that if this was under an angle, I don't have an angle. If this was under an angle, the normal force would not be pointing up. The normal force would be pointing normal. This is my normal force. Wait, but my gravity is acting to put like a gravitational force that we call, well, I would call it gravity, force due to gravity. But because it's such a common force, people call it weight. So either way is fine. I'm probably going to use FG whenever you see me. But weight, just to confuse it, mass and weight are not the same thing. Mass is what keeps something from accelerating. Weight is gravitational force. So that means if I ask you, is your mass going to change on the moon? Which I'm not going to, because I feel that's like a cheap trick. Your mass is not going to change on the moon. Your weight is going to change on the moon. All right, fine. So, back to this. Wait, we were saying it's equal and opposite. It keeps it from falling through. Well, that means that this part, this component of the normal force is equal and opposite to the weight. Well, but we still have a component, and it's this one. We still have that one. This one is equal and opposite to the weight. What about that one? All I did is I said, well, the components have to, like, this is an x direction, these components cancel out. There's still another component. And it's not canceling out. That's what makes my object slide down. So it's, again, it's a systems force, if you want, because it kind of confines it, right? It says it can only slide down that way. It cannot slide down this way. So it's a tool, if you want. It's not a real, like it's not a physical force. All right, so normal force. We're going to come back to frictional forces next time. Tension force is another weird one in that it's a tool that allows us to simplify things. It allows us to simplify geometry. Imagine here was my object, and now I have another object here. And I want to know, how does it pull? Like, this one is pulling down, and so this one is pulling down. Which one is going to go up? Which one is going to go down? I connect them by a string over pull. So now, if this one is heavier, it will go down this way. If this one is heavier, it will go down that way, right? So we want to find out which one goes up, which one goes down. This is a complicated system because now we have to take this y motion, but it's coupled to that weird angular motion, like not angular, motion under an angle. So that's why we're introducing tension. Tension allows us to take all the string away and just keep the forces. And so the string means that like whatever happens in the string will not stretch it, will not change it, So that means that all the force was propagating from here to there. Tension force is a tool that lets me ignore all the problems that are coming up with elastic materials. Okay. So it's unstretchable and it's massless. What would happen if it had a mass? Then the acceleration of the whole system would be messed up. Okay. So we're going to do that one next time. All right. So in summary, we have shown we have calculated with components of forces and components of motion. We found that it's not different from one-dimensional motion. We're going to introduce many more real forces. I would say friction, drag. We're going to basically populate our zoo of forces for the rest of the semester. There's always going to be, oh, there's a new force. Well, it's going to cause the same, like we're going to use the same tools to describe what kind of motion it causes. Right? So we're going to be stuck with motion from forces for a long time because that's all that mechanics is about. So questions about this? No questions. All right, if there are no questions, thank you for coming. Have a good long weekend and see you next Thursday. You saw the... Yes, there was something wrong with Sophia's key, but it's set to C. I didn't know that you can see the answer. You can see your final result. You should be able to see your final result. Okay, so yes, you are correct. Something is wrong with the quiz. I couldn't change it while you were taking it. And it doesn't allow me to type in what kind of answer it was. We just have like a button. This question, yes. Quiz question, no. Yes. So if you look at my recitation, you will see the question and the answer. Yes, I don't need to take pictures. All the stuff that will be on the board will be in the slide. Oh, you didn't post the answer after 11:34. So the way that I do it, I go through the answers and the timestamp. I told people at 11:34 that this is the correct answer. And so all the answers before I will consider the ones afterwards. But it's fine. We're taking an average of all the correct answers that have given over the whole semester.